So in the last few lectures we have been discussing about models, and we have discussed many models: random graph model, right, Watt-Stockett model, ring lattice model, then Barabasi-Albert model, then price model, right. And Barabasi-Albert models, price model, these models are sophisticated in the sense like they are able to produce networks with power law distribution, right. But if you think of the mechanisms, they basically follow preferential attachment policy, right, or cumulative advantage policy. So cumulative advantage policy basically says that each node will get richer over time. But if you think of and this rich gets richer phenomena, this is applicable to social networks, right. This is applicable to citation networks, but this may not be applicable to biological networks like protein-protein interaction networks, because there is no such compulsion that a protein will interact to another protein, right, with high degree. Okay. So therefore, although you explain the power law degree distribution, you may not be able to realistically explain a biological network, a growth of a biological network which also follows power law, right, using Barabasi-Albert model. Therefore, people started thinking of different other mechanisms by which you can also generate a power law, a scale free network, but not following the preferential attachment policy. Okay. So in this particular direction, John Kleinberg, right, he is a computer scientist in Cornell. So John Kleinberg in 1999, who is also the inventor of Hertz algorithm we discussed in the last chapter. Okay. So he proposed this model called vortex copying model. Okay. Now what is vortex copying model? Vortex copying model is a very unique idea. The idea is that when a new node joins, so this new node V joins, right, and let us assume that again V has m number of outward edges, right. So when V joins, V will not get attached with other nodes based on the preferential attachment. Okay. Instead, what V will do, we will choose a node, an existing node uniformly at random, right, and starts copying that node's edge distribution. Okay. Let us say V has randomly chosen U as the node which V wants to copy. Okay. So say U is connected to X, U is connected to W, U is connected to Y, right. So V, then what we will do? We will also select X, W and Y, okay, but V has only two nodes. So among these three nodes X, W and Y, we will choose two nodes. So let us say we will choose X and W, and V will be connected to X and V will be connected to W. So what happens? What has happened? V basically has copied U's edge, the edge distribution that U follows. Okay. Now you may argue that, okay, what happens if V has say degree 4? So V would first choose U and V will be connected to X, W and Y, and there is one remaining edge. What we will do? We will choose another node from the remaining node set, again uniformly at random, right, and starts copying one of its edges. For example, let us say V has chosen W, okay, and a W is connected to X, Y and this node. So this is M, let us say. Now V is already connected to the X and Y, so V will not be connected to X and Y now, then V will be connected to M. So this node, this edge will be connected to M. Okay. So what is the idea here? So you basically choose uniformly when a new node joins with degree M, you choose you basically choose uniformly at random from the previously chosen vertex M, right, replicate those links, and if you are exhausted with the links, if some edges are still there, you keep on repeating the same thing again and again. Okay. So this is called vertex copying model. Now, I am not going to the theoretical details of it, but if you look at the theory, it also proves that this model would eventually generate a network which follows power law, but this is a non-preferential attachment based model. Okay. So, now let us look at some other models, right. So, we in the preferential attachment models we discussed the other limitations. For example, there is no notion of competition, there is no notion of decay of prestige over time and so on and so forth. So, later on several models have been proposed. One of such models is this local world network growth model. In this particular model, the intuition is that that when you compute preferential attachment, when you compute PD, right, which is D divided by the total sum, right, that particular quantity PD, it should not be based on the entire network, it should not be a global property. So, in Barabasz-Albert model, Price model, we assume that we calculated PD based on the entire network, okay. But many times the entire networks are not available beforehand. And the second reason is that, say for example, in case of citation network, right, in citation network when a paper in the field of say AI, right, joins the system, right, it is less likely that the node will cite a paper from say database or the paper from a theoretical algorithm kind of paper. So, what the paper would do? The paper would essentially look at the other papers which are published in the AI domain, right, and based on the preferential attachment probability with respect to that particular domain, the new node will choose another node. What I mean to say is that when I write a paper in the area of AI, right, I will only look at those highly cited papers in the area of AI and then I cite. It is not that I will look at the citations with respect to all the areas, right. So, the idea was simple here. The idea was that this PD should be calculated based on the local property, not based on the global property. Okay. Another model is called the network model with accelerating growth. Okay. It basically says that so far we assume that the PD, the probability of a node with degree D is proportional to D, which is linear, right, but it may not be linear, it may be super linear, right. It may be PD is proportional to D to the power say D square or D cube, right. So, in fact, this World Wide Web citation networks, right, if you look at the actual growth, they actually follow superlinear growth model. So, linear growth model may not be enough. Okay. So, people then try to come up with superlinear, in fact, sublinear growth model also, hybrid model also, right. There is also another interesting idea of aging effect, okay, recency effect. What is aging effect? The idea is that as the node becomes older and older, it starts reducing its importance. And I mentioned in case of say actor-actor network, right, in general actor actress when they become older, it is less, I mean their popularity will also reduce in general. Okay. So, this aging effect can be quantified separately into the preferential attachment model, right. So, this when you calculate PD, there should be some quantity which should be inversely proportional to T, right. As T grows, as T increases, PD should decrease. So, this is called aging effect, and one needs to consider this aging effect explicitly into the growth model. In fact, there are also models which in fact in the aging model, or what people suggested is that let us make it time dependent, because the factor that I mentioned, this is time dependent. Okay. So, then this total attachment probability, right, of a node with degree k should also be dependent on T. So, this function is essentially a function of both k and T, and this function which is a biparametric function, this can be split into two other functions, which is a function of k times the function of t. Now you define f and t, based on your applications or based on your assumptions. Okay, this is aging model. So there is another idea called short-term memory preferential attachment. So here, the idea of memory actually comes into the picture. So the idea of memory is that, so it basically says that when you calculate preferential attachment probability, you may want to forget about older citations or older ages, right. What it basically says is that as the time moves, okay, say a node initially had got a lot of ages, right, those ages should not be considered at the current time period. We should ignore the prestige when the prestige which this node had received long time back. Now this factor is important because this factor now enables the notion of competition, right. So once you start forgetting about the old prestige, you basically allow the new nodes, right, to kind of compete with the old nodes, because old nodes now do not have that much prestige, right, because some of the prestige has now gone. So the notion of competition will come, and the new nodes will also have advantages to acquire edges to increase degree over time. Okay. So this was also proposed. So there are many other network growth models which I have not mentioned here. People looked at not only the power law distribution, right, but also other factors. For example, in one of our research in the lab, we showed that in case of citation network, if you look at the fine grained citation distribution of nodes, right, if you think of different types of papers and their citation growth, you essentially you can think of 4 or 5 patterns. For example, there are papers which starts receiving citations immediately after publications. You can think of this kind of growth and then decrease over time. There are papers whose citation increases over time, papers like transformer. Okay. There are papers which do not receive citations at the initial stage, but later it gets popularity. So these kind of papers are called sleeping beauties. Okay, sleeping beauties. So sleeping beauties are those scientific papers which do not receive enough citations in the initial stage of their career, right? Their timeline, first 5, 6, 7 years, but after certain time, people start realizing the importance of those papers and the importance grows over time. Okay. So this is basically increase and then decrease. This is continuously increasing. You can have also patterns like which decays over time, right? And this pattern you see that after certain point in time, the citation starts increasing, then decreasing, and so on and so forth. Okay, monotonically increasing, monotonically decreasing. So there are essentially 5, 6 patterns. Okay, and a citation network growth model. And in general, if you combine everything, you will of course get this kind of distribution, power law distribution. But when you magnify this one, right, you will get 5, 6 types of distributions, right. Interestingly, none of the growth models, including Price model, Barbour-Selbert model, would be able to mimic the 6 different patterns. So we showed that, okay, let's try to come up with a model which includes the aging factor and other factors as well to mimic this 6 different patterns. But there are many such actually research happened in the past which basically suggested us how to generate synthetic networks. So we stop here with the takeaway that these kind of models would be very handy, would be very useful when you want to test your own algorithm on small networks, and these models will essentially give you flexibilities to generate networks of different sizes, and you test your algorithm on these networks and you freeze one model, one algorithm which seems to be effective compared to other models, and then you move that algorithm to the production level. Okay, therefore, this chapter is very important. With this, I stop here. Thank you.